Okay, in the next problem we have to solve, we have a piston cylinder device initially contains 0.3 kilograms of nitrogen. This is cool because nitrogen can be considered as an ideal gas, so we don't have to use a table and we can use our ideal gas law. What do we know? We have temperature T1 190 degrees C and we have the pressure P1 130 kilopascals. Now, this nitrogen will experience an expansion process, okay? So we know that the piston will move up, leading to work out, so anticipate that the work will be positive. And the process here is isothermal. This gives us an indication that T2 should be equal to T1. And this will lead our nitrogen to a final pressure of 75 kilopascals. What we need here, we need to calculate the work in kilojoules. So this is problem 4.3. Let's sketch this. What do we have? We have state 1. Okay, we have a piston cylinder assembly. Inside here we have our nitrogen gas. And what do we know? We know that P1, this is given, is equal 130 kilopascals, and T1 is equal to 190 degrees C. Then we have state 2. At state 2, we know that there is an expansion process, so the piston will move up to a second position here with our nitrogen inside. And what do we know? We know that P2 will be equal 75 kilopascals. And we are given that this process between state 1 and state 2 is isothermal. So therefore, the temperature remains constant. So we can express this as T2 is equal to T1 is equal to 190 degrees C. What we have to get the work. The other thing that we are given that remains constant between the two is the mass of our nitrogen is 0.3 kilograms. So, computation of the work 1, 2. So what do we know? We know that the work 1, 2 is equal to the integral 1 to 2 of P dV, right? But here we are dealing with an ideal gas. So, but PV is equal to mRT. R is the gas constant for nitrogen. So therefore we can write that P is equal to mRT over V, that we can plug here. Why we are doing this? Because you see that T will appear here, the temperature, and since we know that this is an isothermal process, we can bring the temperature out of the integral. So this is equal to 1, 2 of, we said, mRT cross dV over V, okay? So the mass is constant, this is a gas constant. The temperature is constant because it's isothermal, so we bring all this group out of the integral, leading to mRT T1. Integral 1 to 2 of dV over V leads to ln V2 over V1. So what does it mean? If we get the value of V2 and V1, we can plug them here and calculate our work. So at state 1, what do we have? It's an ideal gas, so this is P1. V1 is equal mRT1. So this is equivalent to say that our V1 is equal to what? Is equal to mRT1 over P1. They are all given here, so we just have to plug our values. we have the mass 0.3, we have the gas constant for nitrogen 0.2968. You get this value from here, and T1 in Kelvin, this will lead us to 463 Kelvin over the pressure P1, 130 kilopascal. And this volume V1 will be 0.3171 cubic meters. So this is done. We do the same thing at state 2. Exactly the same process, so I can just bypass this one and write that V2 is equal directly to M R T2 over P2. We are given P2, and we know that T2 is equal to T1. So same thing, we have 0.3, 0.2968, cross the temperature, which is 463. Now the pressure P2 is lower, is 75 kilopascals. So this will give us a value of 0.5497 cubic meters. V2 is higher than V1. It makes sense. We have an expansion process. So now we just plug this one here. We plug this one here. We have the mass, we have R, we have T1, 463. So this will give us directly the work. So the work 1,2 is equal to what? Is equal to the mass cross the constant, the gas constant, cross the temperature, T1 or T2, doesn't matter, it's isothermal, ln V2, 0.5497 over V1, which is 0.3171. And this would give us a work of 22.68 kilojoules. And again, here the work is positive. It makes sense. We have an expansion process. This is a work out, and it has to be positive. There is another way to solve this problem, which is more systematic, where we can bypass the calculations of V1 and V2. So when you reach this step here, what you have to say, but we know this is an ideal gas, right? So we know that PV is equal to MRT. So therefore I can write the volume MRT over P, right? And now what we can do, we can plug the values here. So this will be MRT1 ln of, okay, our V2 becomes MRT2 over P2, right? And our V1 becomes MRT1 over P1. The same mass, same gas constant. Interestingly, we have isothermal process. So this would give us MRT1 ln of P1 over P2. And this one is more systematic because we are given the mass, we have the gas constant, we know T1 and it's isothermal, but here we are given P1 and P2. So we just plug the values and calculate this without calculating V1 and V2. If you plug the values, you get exactly the same value of plus 22.68 kilojoules.